Welcome everyone to the second in a series of SEAM webinars. Tonight, John J. Lee will be presenting his presentation, and with that, I will let him take over. Thank you.
Morning, thank you. Thanks for the introduction. So today my presentation is velocity model building and migration using the SEAM Subsalt Earth model. So this work is together done with my collaborators and team members from velocity imaging and elastic weaving fluid viewing shot. And we are from Group Research and Technology, PDNT Division and Petronas. So my name is John Lee, and here is my email. So before I start my presentation, I would like to give a basic introduction of who we are and where we're from. So we are the Group Technology and Research GINT and Project Delivery and Technology PDNT Division Petronas. And Petronas is located in Malaysia. If you don't know where exactly Malaysia is, the right picture shows a bit of the map where Malaysia is. So the dark green color shows the map of the Malaysia, which is located in the Southeast Asia. So most of the subsurface projects that are under Petronas is in a Geoimaging Technology department. So the projects that are under Geoimaging Technology can further be categorized into the three groups. The first group is the velocity imaging and elastic wave field view in shot. So the view team is currently working on the fast true amplitude imaging and fast AI velocity model building together with target-oriented prospect imaging. And the next team is called Physics Fluid Prediction using artificial intelligence, the PI in short. So the PI group is currently working on the rock physics repository and data-driven reservoir properties prediction and well phases prediction and stratigraphic correlation. And the other group is called Subsurface Insights, SI in short. So the SI is currently focusing on the seismic feature recognition and extraction and sweet spot identification and the geology-driven interpretation. So our target of this geoimaging technology in current stage is to develop a whole workflow of machine learning-based data-driven fluid physics sweet spot prediction. So as we can see in this picture in the center, so the underground structures that we are dealing nowadays are mostly very complicated, which it contains the subsalts, the gas cloud, or the complicated faults and so on. So the SEAM Subsalt dataset actually is considered as an ideal synthetic dataset that we can use to validate the algorithms and methodologies that we have developed or are being developed in our groups. So actually the SEAM dataset, Subsalt dataset has been used in all three groups, but in today's talk, I will just focusing on the view projects, which are the imaging and velocity model building. So as we can see here, this is a bit of the map of the view imaging workflow. So first of all, we have initial input, which can either be the migrated stack plus the seismic attributes or the shot gathers. So the input will be put into the next stage, which is the seismic geology properties collaboration, which contains horizons and faults detection, the well ties, as well as the semblances, and so on. And the next step, which is colored in yellow here, is the velocity model building procedure, which contains the AI-based velocity model building and the uncertainty analysis. So this procedure will generate a predicted velocity, initial velocity model. And if this initial velocity model is good enough, then we can directly move it to feed it into the final step of migration. And the migration will finally output a final subsurface imaging. So alternatively, if this initial velocity model is not that good enough, usually it happens in the real data case. So we will have to feed it into the our new developed the Anisotropic FWI procedure, which is here. And then the FWI will do some more updates of the velocity model so that it can finally be fed into the migration procedure. So I will start to introduce this yellow box, which is the artificial intelligence velocity model building. Also contains the uncertainty analysis. So our artificial intelligence velocity model building is mainly focusing on based on the hybrid physics-guided neural network, HPGNN in short. The related papers are published in geophysics in 2020 and 2021. So the term, the hybrid, means a combination of the CNN together with RNN. So here is a bit of the map of how it works for the HPGNN. So as the input, we will have the shot gathers, which are from thousands of velocity model training models. And the shot gathers will be fed as input to be fit into this neural network so that it will generate the predicted velocity models. And here, this is our first Misfit, the model-based Misfit. And then the predicted velocity model can thus be fed into our RNN network. And then it will generate the modeled shot gathers. And here, the difference between the model shot gathers and the input shot gathers will be our second part of the Misfit, which is the data-based Misfit. I'll just break down the procedure and to make some details of this CNN RNN network. So here, this is the picture of a breakdown part of the HPGNN. The first part is the CNN part. So as we know that the input of the CNN is the shot gathers, and then we put these shot gathers into our convolutional neural network, and so that we can get the predicted velocity models. So these predicted velocity models, the difference between these velocity models with the ground truth velocity model will be the model-based Misfit. We denote it as LM. So the LM can be calculated by this equation, which are based on the L2 norm. And the next part is the output of the CNN will be the input of RNN, so that the predicted velocity model will be fed into this recurrent neural network to do the forward simulation, and then we can get modeled shot gathers. And the difference between the modeled shot gathers and the true shot gathers will be the data misfit, the next part of our whole misfit function. So the data misfit can also be calculated by this autonomous equation. And then back and forth, this is how the HPGNN do the training work. So the first thing that we have to do is to generate a set of the training models. So here I illustrated two different kinds of training sets, the training set number 1 and training set number 2, which contains the subsalt in the velocity model. And the difference between the training set number 1 and training set number 2 is for the training set number 1, as we can see, the background layers are much closer compared to the training set number 2. So in the training set number 2, the background layers structures are more finely layered compared to the training set number 1. So by comparison of these two training sets, we would like to know the performance, the influence of the training sets on the final prediction results. And then we can use the generated velocity models to generate the short gathers. So the lower picture shows the short gathers that are generated from the training set number 2. And then the short gathers will be fed into the CNN workflow, and then will generate the predicted velocity models, which will feed into the RNN and back and forth to do the whole procedure of training. So after the training reached to a point where the whole misfit, which is the data misfit plus the model-based misfit, reached a very small value, and we are satisfied with the result. So we can use the things like the data set or the real data set to do the validation. So here is a 2D example of using the same data set to do the validation. So the first row shows the cross-line section of the scene that are extracted from the SIM 3D Subsalt model, which are considered as the ground truth velocity model. And the second row to the fourth row shows the predicted result by using different training set and different frequency band. So the second row shows the training set when we are using the training set number 1 with a dominant frequency of 15 Hertz in the RNN procedure. So as we can see here, actually the prediction result is not as good as the row number 3 and number 4. So row number 3 is the result that we are using training set number 2, which has much finely layered background structures. So, and the dominant frequency is 15 Hertz during the RNN procedure for the third row. As we can see here, most of the top part of the salt body has been predicted. So we increase the frequency from 15 Hertz to 20 Hertz, and to see the result, which is shown in the last row. As we can see, compared to the third row, the most of the salt body are now being predicted. So theoretically, by increasing the frequency, dominant frequency in the RNN procedure, it will kind of get a much satisfying prediction result. So here is just the 2D prediction result, and we only have one line of the short gather, one line of the receivers, which will be put here. So we believe that after we expand the 2D into 3D, the coverage of the of the receivers will further increase the prediction results. So here is a comparison of the short gathers. So the first row shows the ground truth short gathers from the SIM 2D velocity pictures, and the second row shows the predicted velocity short gathers by using the training set number 2, and with a dominant frequency of 20 Hertz. And the third row shows the difference between the training set, between the true shot gatherers and the predicted shot gatherers. Now we further expand the HPGNN into 3D HPGNN. So first of all, we expand the 2D training velocity models into the 3D training velocity models, and then we feed them into the HPGNN and do the training work. And then here is the validation stage. So for the validation, we crop the same 3D velocity model into small pieces of the cubes of the velocity model, which is shown in the right-hand side. Just one picture, one of the same pictures, small cubes. So red color denotes the slots, and the left-hand side picture shows the shot gatherers with respect to the ground truth velocity model, same velocity model. By comparison, we also tried use the CNN neural network to do the training. And the left picture shows a Misfit comparison when we only use the CNN, which we have been using like 4K training samples in the CNN to get this kind of a loss curve. So on the right-hand side, we use the HPGNN to do the training, and then, but in this picture, we only use, in this diagram, we only use 1.5K training samples, which can save a lot of processing time compared to the CNN to get this loss curve. So here is the 3D validation of the same data set. So on the left-hand side, we can see the depth slides, the inline and cross slides of the same ground truth velocity model. And the right-hand side shows the HPGNN result. Compared to the ground truth velocity model, as we can see, the shapes of the swords are mostly predicted. Even inside of the swords, the anomaly of the velocity can be predicted. And also there are some layered structures in the background. And here are a bit more of the comparisons from different locations of the scene. The upper picture shows the comparisons of the depth slides with the predicted results. And the lower picture shows the comparisons of the cross-line ground truth to be compared with the predicted results. So as we can see here, the overall SSIM value can reach up to 80%, which is considered as a very high precision. So here we also illustrated the comparisons of the shot gatherers. So this picture shows the shot gather of the same ground truth, and the upper pictures, the B and C, show the CNN results. The B is the CNN predicted result, and the C is the difference between the A and B. So to make a comparison, the lower pictures show the HPGNN result of the D, the predicted shot, and E, the difference between the A and D. So compared to the RMS error, we can see the HPGNN performs a better job compared to the CNN prediction results. So after this procedure of AI-based velocity model building, so we can get a initial velocity model. So this initial velocity model will be fit into the FWI to do the further updating of the velocity model. So, which is the second part I'm going to talk, the 3D anisotropic FWI. So, because in the current stage, the seismic imaging and inversion, but the challenging part is we have to deal with a lot of complicated structures, such as the subsalt. So to build the subsalt model is, in the conventional way, is very labor intensive and also very time consuming, also will introduce a lot of human misinterpretation. So our target is to try to use the regularized FWI plus the automated salt flooding to reduce the human intervening, and so as to reduce the human misinterpretation. And also we have considered the seismic anisotropy into the whole workflow. So after the regularized FWI and automated salt flooding, which will be processed in the isotropic FWI, then we will put the updated result into the anisotropic FWI to do some more updates. So here is the first part of our anisotropic FWI, which is the regularized FWI, the FWI plus TB. So as we can see in this function, so the first term is the conventional FWI, which is based on the model, the data-based Misfit. In the new Misfit function, we added a new term, which is the TV regularization. So the lambda TV denotes the regularization parameters, and the TV regularization can promote the limited variation regions so that it can recover the top part of the salt, which can be seen here in this updated velocity model. So after the FWI plus TV, we can continue on the next step, which is the automated salt flooding. So the automated salt flooding equation is shown here, where we have added a new term, which is the flooding regularization, which is quite similar to the TV regularization. So the lambda F is the regularization parameter, and the aim of the automated salt flooding is to penalize the velocity drop with respect to the depth, so that it can recover the deeper part of the salt, which can be seen here. As we can see, compared to the regularized FWI, the salt body, most part of the salt body has been recovered. So then after this FWI plus TV and automated salt flooding, which is done in the 3D anisotropic FWI, then we can feed the updated velocity model into our anisotropic FWI engine, which contains the anisotropic parameters. So the new anisotropic FWI, in our engine, we will use a new approximation of the pure P wave, which is shown here. We have the a new term introduced here, which is related to the epsilon, the Thomson parameters. So after we get this equation, we can calculate the gradient of the P wave velocity, which is shown in this equation, where the gradient of the P wave is related to the anisotropic parameters of the vertical P wave velocity, the horizontal velocity, together with the V and normalized, the NMO velocity, so that we can do further updates to get the final velocity model. So here is the application of the same Subsalt velocity model for the 3D anisotropic FWI. The left-hand side, we can see the true sim velocity model, and the right-hand side shows the initial velocity model that are based on the AI velocity model building. And before we proceed with the anisotropic FWI, we have done a round of smooth so that we can destroy the part of the salt body, so that in order to avoid from avoid falling into the local minima when we do the FWI. So here is the result of the TV regularization and salt flooding. As we compared with the initial velocity model, we can see the most part of the salt has been recovered, and also we see some layered structures. And then this updated velocity model will be further fitted into our anisotropic FWI. So as we can see here, this is the final results of the TTI FWI. As we can see here, the detailed structure information, and even if in the under the salt or outside of the salt has been inverted compared with the isotropic FWI. So to make further validation, we also have two validation wells, the well A and well B. So the well A is outside of the salt, and well B is penetrating inside the salt. And these two diagrams shows the velocity model comparison with the true sim velocity model. As we can see, the red color is the inverted velocity model, and the brown color is the true velocity model. They match quite well even in well A and well B. This can also be seen here in the comparison with the inverted velocity model together with the true velocity model. So most of the part of the detailed structures has been recovered. So after we get the satisfied updated velocity model, then we can feed the velocity model into the migration part, which is our final part of the imaging. So here we are using the new developed TTI anisotropic reverse time migration to do the migration. So in the conventional RTM, when we do the forward and backward simulation, if it's in the elastic wave field, so the SV wave will be inevitably influence on the final cross correlation, which will be contributed as a noise, a kind of noise in the image program, in the image process. So our target of this TTI reverse time migration is to obtain a SV with noise-free image by applying a new approximation of the QP wave equation. So here is the new approximation of the QP wave equation, where we have a new term, 1 plus epsilon, and then the lower pictures shows the comparison when we use the new term and without using the new term of the approximation of the P wave. So the left-hand side shows the old equation that doesn't include the new term, which we can see the SV noise in the middle of the snapshots, and in the right-hand side, it's the snapshots after we use the new term. You can see the SV wave noise has been removed. So in order to validate this equation, we have also illustrated the phase velocity with respect to different anisotropic parameter sets, from weak anisotropy to the strong anisotropy. So we also compared different approximation equations. So the black curve denotes the new approximation that we developed, and the red color denotes the exact formula. And also we have the weak formula, and the green color denotes the formulations that is developed by Professor Tariq. And also we have illustrated the phase velocity with respect to different dip angles from 0 degree to 90 degree. So based on the comparisons, the new proposed new formula can perform a fairly good enough job for the phase velocity. And here is a kind of a bonus part, because we can not only develop the new wave equation of the QP wave, and also we can get new pure SV wave. Here is the SV wave phase velocities with respect to different anisotropic anisotropic sets. Okay. So compared with the weak formula, the new formula can perform a better job, even though after the incident angle reaches up to 40 degrees, it is not as good as enough. But compared to the weak formula, it's better compared to the weak formula. So here we illustrated a 2.5D layered model example to show the difference compared to different softwares. So here the left-hand side shows the velocity model that we are using, and the right-hand side shows the shot together comparisons with our accelerator software. So the right picture shows the shot together when we do the forward wave field simulation using the accelerator forward modeling module. And this picture shows the shot together when we use the new approximation. And we can see the difference is in the accelerator results, we have this kind of SV wave noise. So if we take a closer look of this equation, we can find that, so for this equation, it cannot be simulated purely by the finite difference term, because in the second term here on the right-hand side, the denominator, the wave number kx, ky, and kz, it's very difficult to be simulated by the finite difference term. So our procedure is to combine the finite difference with the wave number domain pseudo-spectral method. So the first term of this equation, we will use the finite difference method to do the simulation. And for the second term of this equation, we will use the wave number domain pseudo-spectral method to do the forward simulation. And in both of these equations, we have added the hybrid PMLS to absorb the boundary reflections, where the theta and phi are the memory variables that is related to the absorbing factors. So for our hybrid PML, it can both be processed in both the space domain and the wave number domain. So here is a bit of the comparisons of the pseudo-spectrum together with the finite difference method. So because the finite difference method, with the change of the step lengths, inevitably we'll have kind of a numerical dispersion, which can be found here. That for the pseudo-spectrum method, theoretically it's dispersion-free compared to the finite difference method. And with the underground structures changed from the simple structure to complex structures, the processing time of the RTM varies. So here is a bit of the map of the processing time of the RTM. The isotropic RTM, VTI RTM, TTIRTM, the comparisons between the pure finite difference and pure pseudo-spectral. So the reason that we use the hybrid method is in the TTIRTM, the processing time is considerably faster compared to the pure finite difference and pure pseudo-spectral. So this picture is under the courtesy of the Ge, which is who published the paper in Journal of Geophysics and Engineering in 2013. So here we have the performance shows the performance of the hybrid PMLs compared with different kinds of PMLs. So the first row, the first column shows the CPML results, and the second row column shows the MPML results, and the third row column is the HPML. So as we can see with the processing time, both the CPML and MPML suffer from different degrees of the boundary reflections. But for the HPML, we can see the snapshot is much clearer. And also the left-hand side picture, we can see the shot gathers comparisons, especially in the black curved area. We can see the boundary reflections in both the CPML and MPML. And for our HPML, the advantage is that we can not only be applied in the space domain, but also we can apply it in the wave number domain, which can adjust our new approximation of the pure P wave equation. So here is a bit of the application of the SIM dataset on the TTIRTM. So here we can see the 3D true velocity model of the SIM on the left-hand side, and on the right-hand side is the final results of our 3D SIM TTIRTM results. As we can see, the salt shapes or even in the inside of the salt, the velocity change can be migrated. So this picture shows the input anisotropic parameters in our TTIRTM, the epsilon, delta, azimuth, and dip. And here are some more comparisons of the SIM TTI results. So the left-hand side picture shows the true SIM depth slice of the velocity model. Red color denotes the salt, and in the picture in the middle shows the accelerated TTIRTM result. And the right-hand side picture shows the new TTIRTM result. As we can see, by comparison here, inside of the salt, the new TTIRTM results is much clearer compared to the accelerated RTM, TTIRTM. And here is a comparison of the depth slice. So this is the left-hand side is the 3D true velocity, SIM velocity, the depth slice, the cross-line slice, and in the middle shows the accelerated TTIRTM results, and the right picture shows the TTIRTM results that we proposed. So compared with these two results, we can see the right picture has the fewer noise. So it is also worth to mention that for both of the accelerated TTIRTM and new TTIRTM, we have used the input shot gathers are generated from another software, Geoimaging software, so that we can make sure that both of the accelerator and the new TTIRTM are kind of apple-to-apple comparisons. So then we can make a conclusion for today's presentation. So first of all, in our new view imaging procedure, the first step we are doing is the time-saving artificial intelligence VMB, velocity model building, that involves the hybrid, the physics-guided and neural network, so that it includes both the data-driven and deep learning, and based on our results compared to our results compared to the pure CNN, we can see that our new AI velocity model building has its advantage. So after the AI velocity model building, we can generate a kind of a initial velocity model. So this initial velocity model alternatively can also be fit into our anisotropic Fourier form inversion, so that more details of the structures can be updated. And after that, the updated velocity model can be fitted into our next step, which is the TTIRTM. So, which also has been validated by the Sim3D velocity model. So the whole workflow, by this whole workflow, we can save a lot of time in the velocity model building stage and also in the FWI stage. Okay, so actually we have, after the synthetic sim data set validation, we also have applied the whole procedure into the real data set by doing the velocity model building together with the FWI and RTM. So before I end this presentation, I would like to thank Petronas for letting me present this talk. And also I would like to thank my collaborators from Bosnia, who is the head of the department, and Dr. Dr. Ernest, and Mr. Fidaus and Dr. Hamad Riza for the STA, who are the STAs of our whole projects, and Dr. Hilusa who is the view team leader, and also Daniel and Farah are the team members of the view. And also I would like to thank Professor Jensen, who was previously in University of Calgary and now in Ocean University of China. And also I would like to thank Mahesh Kalida, who is from KAUST. And also finally, I would like to thank SEG and SIM for inviting me for this talk. Thanks. And here is a picture of our whole team. And thanks. I would like to, I'm welcome for any questions. And thanks.
Wonderful, thank you. If anyone has questions, please type them in the Q&A box. I don't see any questions. If you think of questions later on, his email was in the first part of the presentation, and this presentation has been recorded and will be posted on SEG Live shortly.
Yeah,
Thank
for
you.
any further questions, you can either email me, which I think it's in the first page of my slides.
Great. Wonderful. Thank you. Thank you for attending. Bye-bye.
Bye.